Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the VLSI technology. So today in this video we are going to talk about the photolithography process. We have already seen the alignment and the exposure process and the initial processes also in the previous videos. If you have still not watched the previous videos, I recommend you strongly to go and watch the previous videos first and then come to this video. So today in this video we are going to see all of the steps after alignment and exposure. So first of all, in the alignment and exposure we have the standing wave effect. Okay, what is the standing wave effect? The standing wave effect is produced due to the interference of the incident and the reflection lights. Okay, so due to the interference we will be having the periodically overexposure and the underexposure regions which affects the photolithography resolution. So these are very technical terms, so you should understand it with the help of a diagram. So like here we will be having the interference. We have two types of interference. First is constructive interference, second is destructive interference. Okay, so what happens? The standing wave intensity is looking like this. So this is my light intensity and here we have the surface of the substrate. Okay, so now here what you can see, here the intensity is increasing, the intensity is decreasing, and this is my average intensity. Why intensity is increasing? Due to the constructive interference. Intensity is decreasing due to the destructive interference. So due to the constructive interference we will be having the overexposed region, and due to the destructive interference we will be having the underexposed regions. Okay, so now in the overexposed regions we will be having the higher light intensity, so the photoresist property will be different inside this constructive interference region, and inside or below this destructive interference region or underexposed regions we will be having different photoresist properties. You can see here, this is my photoresist. The photoresist will be getting periodic constructive interference and destructive interference. So here I will be having periodic overexposure and underexposure parts, due to which I will be having this zigzag type of region in the edges of the photoresist. Now I have to remove this zigzag portions. So now for that I will be using the post exposure bake. What is my post exposure bake now? So here we are again baking it. So from the name only it is evident that we are having a high temperature process. We are baking our wafer. So the photoresist glass transition temperature is Tg. Okay, we have to bake at a temperature higher than this glass transition temperature or Tg. So there will be thermal movement of the photoresist molecules and there will be rearrangement of the overexposed and the underexposed photoresist molecules. This zigzag type of molecules will be again rearranging and there will be averaging out of the standing wave effect. The standing wave effect will not be there, its effect will be decreasing and I will be getting smooth photoresist side walls and it will be improving the resolution. This is how the post exposure bake is important. If I am using the deep UV radiations, chemically amplified photoresist, then post exposure bake will be providing the heat needed for acid diffusion as well as amplification. For the chemical type of photoresist we require it very much. So now if I have the deep UV chemical amplified photoresist, then post exposure bake is a must process. After the post exposure bake process, the image of the exposed area appear on the photoresist due to the significant chemical change and after the acid amplification. So this is how the post exposure bake is really important part. So post exposure bake is normally uses hot plate at 110 to 130 degrees Celsius for about 1 minute, and for the same kind of photoresist post exposure bake usually require a higher temperature than the soft bake. Okay, if I have done the soft bake at 110, I will be doing the post exposure bake at a temperature which is greater than the 110. That time I cannot take the post exposure bake temperature to be 110, even though it is greater than 110 is greater than the glass transition temperature. Okay, I have to take it greater than 110 degrees Celsius. Insufficient post exposure bake will not completely eliminate this zigzag pattern, and there will be some standing wave effect also present in the wafer when we have insufficient post exposure bake. So we have to do the post exposure bake sufficiently, but we cannot even over bake it, because if we are over baking it, there will be polymerization and it affects the photoresist development. If I am giving very high temperature to the photoresist, it will become the polymer, or it will be becoming hardened out, so it affects the photoresist development process later on. So after the post exposure bake, you can see the zigzag pattern has removed and we get a very smooth sidewall for the photoresist, and this improves the feature size and the feature quality as well. So now coming to the wafer cooling. As I told you, after every heating step we have a cooling step also, so that if our wafer is going to the next process, there will be a normal temperature wafer. We don't have any effect on the temperature of the wafer. So after every heating process we have the wafer cooling stage. After post exposure bake also, the wafer is also again put in a chill plate and we are cooling down the wafer to the ambient temperature before sending it to the development process, because in the development process I will be using the chemicals and I need to maintain the reaction rate of the chemicals, and the reaction rate of the chemicals will be maintained only if I take the temperature to be similar to the ambient temperature. If I have a higher temperature, the reaction will be very faster and I cannot control the higher faster reactions. So high temperature can accelerate the chemical reaction and it can cause overdevelopment and the damage also on the surface. It can cause the photoresist CD loss as well. So now coming to the development. What is development? Development is done with the help of a developer solution. So the developer solvent dissolves the softened part of photoresist. Okay, so if I have the photoresist, there will be some parts which are softened out. Now I have to remove this softened part and I will be using the development process. It transfers the pattern from the mask or the reticle to the photoresist. Okay, so this is how I am transferring the patterns on the wafer. So there are three basic steps: development, rinse and dry. First of all, I will be using the development solution. I will be submerging my wafers into the development solution. Then I will be pulling it out after a particular time that I have removed all of the softened out photoresist. Then I will be rinsing it with the deionized water and then I will be spin drying it. Okay, so what is the developer solution? If I have the positive photoresist, it use the weak base solution, like we have tetramethyl ammonium hydride, or I can say TMAH, which have the chemical formula as CH3,4 and OH. So this is the developer solution for the positive photoresist. Okay, so you can see here we have the photoresist layer. Okay, we have the photoresist layer, it can be positive or the negative photoresist. Then we have the alignment and the exposure process. After that we have to do the etching. The etching is done with the help of development process. Now this is the development process. In the development process I will be using some chemicals to remove this photoresist layer. And after that we have the etching process where I remove the silicon dioxide layer also, so that I will be having this mask. Okay, so this is how I make the patterns or mask on the substrate. So here you can see we have the substrate, we have different development profiles. If the photoresist is completely removed in this mask region, this is the normal development. See here we don't have the full removal of the photoresist, there is a layer of photoresist present on the substrate. This is incomplete development. Okay, in the under development we don't have actually a square type of walls. This side wall is actually tilted. It is lateral type of side walls. This is under development. Okay, in the over development we have removal of the photoresist. So my mask should have looked like a straight line. So side wall should have looked like a straight line, but due to over development, over use of chemicals and more time for development process results in this over development of this photoresist. So I hope now you understood the various development profile. Now coming to the developer solution. For positive photoresist and for negative photoresist, we have different type of developer solutions. For the positive photoresist, I use weak acids like TMAH. In the negative photoresist, we use xylene. So we rinse the positive photoresist developer solution with the deionized water simply. In the negative photoresist, we use N-butyl acetate for rinsing purposes. So now this is the schematic of a spin developer. Okay, so here we have the vacuum. This is the vacuum chamber, and this is the chunk over which my wafer is placed. So here we have the tap type of structure. This is the nozzle actually, which removes the deionized water. It sends the deionized water on the wafer. Okay, similarly here we have a nozzle type of structure which is sending the developer solution to the wafer. So first of all we will be sending the developer solution, and this wafer is rotating. Okay, this chunk is rotating, and also this wafer is rotating. So first of all we are sending the developer solution, then we will be sending the deionized water for rinsing purposes, and then we will be just rotating it for spin dry. Okay, so here we have drain also, so that all of the exhaust gases or residual liquids will be flowing through here. Okay, so now this is the optical edge bead removal exposure. So now here we have a light source. Light source is sending the light on the at the edges of the wafer, so that the photoresist will be removed from the edges, as I don't want any kind of component, the transistor or MOSFET I don't want at the edges, because I want the transistor only at the symmetrical surfaces. At edges we have the sharp changes in the symmetricity. This is the reason I don't want any component at the edges, and I will be removing the photoresist layer from there. Okay, so I hope now you understood this process. I have this light source. I will be rotating this wafer. The wafer is on the spindle, and this chunk, the wafer is present here. This yellow part represents the photoresist, and we are just exposing the ends, and we are rotating it so that all of the ends, this will be having a circumference symmetry. So at all of the ends, full of the circumference, we won't be having any photoresist layer. So now coming to the development solution. So first of all we have removed the photoresist from the ends. Now we will be putting the development solution, so that it will be removing all of the weakened out photoresist from all of the layers which are present. It will be making the patterns on the photoresist. Okay, it is the solution which is consuming the soft photoresist. Okay, so again here we have the nozzle which is giving me the development solution over the wafer. So you can see the photoresist is covered with the development solution throughout it. So at full surface of the photoresist we have the covered development solution. So now again we are spinning it off, and now when we spin it off, it will be removing the softened out photoresist, and we will be getting the mask region. Now we will be rinsing it with the deionized water. So again we are using this nozzle to put the deionized water. We are rotating it. So now we are spin drying it, so that we have removed all of the softened photoresist, we have removed the developer solution, we have removed the deionized water. Now we want to dry it. For drying we are just spinning it at a very high speed. So now our wafer is ready for the next step. So now coming to the development, you can see here we have the developer solution. We are having the developer solution from the puddle, and now this is the wafer, and this is the developer puddle over here. Okay, so if I am using the spin spray for the development solution here, so the development solution here you can see it is a very even structure of the development solution over here. If I am using the spin spray will be giving me an even structure, because when I use the developer puddle, so the development solution was uneven on the surface. Then I just spinned the puddle, and here I will be getting the even structure of the developer solution. Then I spin, rinse and dried the wafer. Now coming to the hard bake. After all of the processes, we have the hard bake process. It will be evaporating all solvents in the photoresist. It will be improving the etching and the implantation resistance, so that now after this the photoresist will be hard to etch. I don't want now the photoresist should be etched away, because this is the photoresist that I require. Okay, so this photoresist I don't want to etch away, so I improve its etch resistance with the hard bake process. It improves the photoresist adhesion also with the surface. It polymerizes and stabilizes the photoresist and the photoresist flow to the fill pinhole as well. So there will be no pinholes if I am using the hard bake process. So you can see here, if I have the pinholes, if I have the thermal flow will be giving me the photoresist to cover the pinhole. So here you can see this was the pinhole. The photoresist will be covering the pinhole if I am using the hard bake process. It will be expanding and this pinhole will not be present here. So again, for the hard bake process, hot plate is commonly used. We are giving the high temperature. For that I require the hot plate. It can be performed in an oven also, and its temperature is 100 to 130 degrees Celsius. Bake time is around 1 to 2 minutes, and hard bake temperature is normally higher than the soft bake temperature for the same kind of photoresist. So whatever temperature I have taken for the soft bake operation, I will be taking the higher temperature for the hard bake operation. So there are again two cases: if I have underbaked, if I have overbaked. If I have overbaked, the photoresist will be flowing away. Okay, it will be flowing away, it will be melting, and there will be bad resolution. If I have underbaked, photoresist is not fully polymerized. Then okay, we want it to be polymerized, we want it to be having high adhesion. That will not be there. So poor adhesion will be there, and we will be having higher photoresist etch rate as well. Okay, so now coming to the photoresist flow. This is how photoresist will be flowing. So over baking will be giving me the photoresist flow. It affects again the photolithography resolution. So here you can see this was the photoresist. It will be flowing into the masked area or the patterned area if I am using the higher temperature. So in the normal baking, you can see we have a very smooth area, but in the over baking we have this flowing of the photoresist. So this must be avoided. So now if wrong photoresist is refilled into the spinner, what it could be having as a consequence? So each photoresist has its own sensitivity and viscosity. Okay, if I don't know which kind of photoresist I am using, then I don't know what type of sensitivity it has. Second, I don't know what kind of viscosity it has. Okay, then I cannot choose what spin rate I will be setting. I cannot choose the ramp rate, and the time, the baking time, the temperature, everything depends upon the type of the photoresist. Exposure intensity, exposure time, developer solution, development condition. So pattern transfer process will fail itself. I should know what kind of photoresist I am having. Actually, if I am having positive kind of photoresist and I am thinking it is negative kind of photoresist, then everything will be different for positive and negative kind of photoresist, and I cannot use any of the two processes which are in the positive kind of photoresist or in the negative kind of photoresist as an exchange. So this is how I should know what kind of photoresist I have. So now coming to the pattern inspection. Okay, so if the pattern inspection giving me the failure as the result, again we will be stripping off the photoresist and rework on the entire process. The photoresist pattern is temporary actually. We are, if etching the silicon dioxide layer in the wrong pattern, then the wafer is completely of no use. Okay, so first of all I will be inspecting thoroughly at the photoresist level only. After the photolithography I will be having a thorough inspection, and then only I will be moving towards the ion implantation or the etching processes. Photolithography process can rework, but if it cannot rework after the etching or the ion implantation process, so we require a good quality scanning electron microscope microscope or we require the optical microscope. Why can't optical microscope be used for the 0.25 micrometer feature inspection? Because the light, I hope you remember what is the wavelength of the light. The feature size, the feature size 0.25 micrometer, it is 2500 angstrom. It is smaller than the wavelength of the visible light. Okay, an optical microscope works on the visible light itself. Visible light wavelength is starting from 3900 angstrom to 7500 angstrom. 3900 is for violet, 7500 is for red. Okay, so if I have to check a feature size of 2500 angstrom, I cannot check it through the optical microscope because it is having the higher wavelength. Okay, it works on the higher wavelength. Now coming to the electron microscope. So here we have the electron beam. Electron beam is falling on the substrate. Okay, so we can have the electron microscope to determine the feature size which is lesser than the 0.35 micrometer as well. So here we will be having more secondary electrons on the corners. Okay, so here you can see at the corners we are having these electrons to be reflected in these directions also, because at the corners I will be having the sharp edges and it will be changing the reflection direction, and we will be having less secondary electrons on the side walls. So this is how I will be calculating where is my side wall, okay, or the plate surface. So now pattern inspection is used for the overlay or the alignment purposes. Now we can have different type of alignments. We can have various problems actually, like run out, run in, reticle rotation, wafer rotation, misplacement in x direction, misplacement in y direction. We can have critical dimensions. I will be showing you all of the pictures, don't worry. So we can have surface irregularities such as scratches, pinholes, strains, contaminations. We have to check all of the things in the pattern inspection process itself. So this is the run-in. So here you can see this was the pattern, the wafer is moving, so the pattern is moving in the opposite direction. So in the run-out also the wafer is moving and the pattern is moving in the opposite direction. So this is condition on the movement of the wafer. If I have not placed the wafer according to the actual alignment of the printer, so now I will be having run-in and run-out problems. Then we have reticle rotation. If the reticle has rotated or the printer has rotated, you can see the pattern has also misaligned. You can see the misalignment with respect to theta. So misplacement in the x direction or misplacement in the y direction also gives me the misaligned patterns. Now you can see the critical dimension. If I have the photoresist, underneath the photoresist we have the actual layer where we wanted the photoresist. This is the good critical dimension, which means this is the actual area where I wanted the photoresist. Now here if I have extra removal of the photoresist, this is called critical dimension loss. Here you can see we have the extra removal of the photoresist from the middle part, and you can see this is the CD loss over here. Then we have the sloped edges. If the edges have been sloped due to the overuse of developer solution or overheating or any other reason, there will be sloped edges. So now you can see when we have sloped edges, the patterns will be smaller than what we have required. Okay, so if the wafer passes the inspection, then they will move out of the photo bay and they will be going to the next process step, which is either etching the silicon dioxide layer or we can directly send it for the ion implantation process. So these are the references. I hope you understood each and everything. If you still have any kind of doubt, please put the doubt in the comment and I will be trying to resolve your doubt as soon as possible. I hope you like this video. If you like it, please push the like button, subscribe to the channel and also share it with your friends. Thank you so much.